Okay, students, we are going to talk about our last topic in this chapter, which is complex ion formation. This is talking about our transition metals. So remember that middle center D block of our periodic table. Our transition metals are good Lewis acids. Remember that means they like to accept lone pairs. They usually would like to bond with water molecules to form hydrated ions because water is a Lewis base. Remember, it's got those two lone pairs on that oxygen that like to donate to the transition metal. So in this case, here's silver with two waters. It is going to give those two waters, it's going to lend those two electron pairs to the silver, which is our Lewis acid, to get this silver hydrated compound. We call these complex ions. So ions that form by taking some cation with several anions or several neutral molecules are called complex ions. The things that are attaching to our central transition metal we call a ligand. So water in this case is a ligand. It is attaching around the outside of our silver. If some ligand is added to a solution, and that solution, that ligand that is formed, does a stronger bond than our current ligand, it will replace the ligand. So here we have silver and water. We're adding ammonia. Ammonia is a stronger ligand than water is. And so it will actually kick that water out and it will add the ammonia in. So the ammonia now will become our ligand and our water will come out. Generally, when we write our equations, we don't actually include water because we know, so that silver plus there, that actually is a sulfur water complex ion, but we don't write it that way. We just write it as silver plus because we know it's not a very strong ligand, it will easily kick out, and therefore we can just write it as silver plus ammonia will give us that silver ammonia complex. So we can write our complex ion formation reaction, which would be our ion plus our ligand to form some complex ion. So silver is our ion, ammonia is our ligand. We're going to get this silver ammonia complex ion. We can write our Kf. So K, once again, is our equilibrium constant. This is our formation constant. So how much do we need? What will our K value be in order to form this new ligand? So once again, it is our products over reactants. That's a great thing about K. It's always going to be products over reactants. Since these are all aqueous, they're all going to be in our expression. So we're going to have our complex ion divided by our ion times our ligand to give our Kf. Thankfully, we once again have a table of formation constants. It also tells you how many of each you need. So if we look at the top right, if we look at that copper ammonia, you see that you're going to need 4 ammonias to combine with 1 copper, and it gives you the Kf value. That'll be important when we start writing these equations. So here's a problem. It says you mix 200 mils of 1.5 times 10 to the negative third molar copper nitrate. So you have a solution, you have 200 mils of copper nitrate. It is 1.5 times 10 to the negative third molar. You then have another solution. So you have a separate beaker that has 250 mils of 0.2 molar ammonia. What you're going to do is you're going to mix those two together. We know that that copper is going to give us, what's going to happen with the copper is it's going to combine with the ammonia to give us this complex ion, this copper ammonia ion, which is actually, once again, we're still looking at the top right of this table. This copper ammonia, right, complex has some Kf value. So we are going to get this copper ammonia complex. But what will happen is we will still have some copper left in solution. We need to figure out how much of that copper is left in solution when we reach equilibrium. See that equilibrium? That means an ice chart, right? Okay, so what we need to do first, let's see. Well, we could first write our expression, right? Write our equation. What's happening? So in this case, we only care about the copper and we only care about the ammonia. So copper 2 plus from the copper nitrate is going to add with ammonia. You might not know how many ammonias you need, and that's okay. Because we can look at our chart and it tells us that we're going to make copper, ammonia, and we need 4 ammonias for each nitrate. Or for each copper, sorry. So then we can put a 4 in front of our ammonia. So make sure you do have a balanced equation, that you have your ion, which is going to be one of our transition metals, with some ligand will give us this complex ion. So that should be your equation. Look at your table. What is my Kf value? Kf here is 1.7 times 10 to the negative 13th. That is what my Kf value is. Then we had 2 separate beakers. Those 2 beakers we need to mix together. So when we mix those together, we're going to have a new concentration of each of our solutions. So first, let's look at our copper one. Our copper solution, it started as being 200 milliliters, so they changed that to liters. So 200 liters, 0.2 liters times the initial concentration, that will end up giving us moles of copper initially. They're going to divide that by the total volume. So the total volume is 0.45 liters. So our initial copper concentration is 6.7 times 10 to the negative 4th molar. You need to do the same thing with your ammonia. So your ammonia, we had 250 mils, which is 0.25 liters. Multiply that by 0.2 moles per 1 liter, because that was the initial concentration. That will give us moles on top, and we're going to divide that by the total volume. So we get 0.11 molar is our initial ammonia concentration. Once we have those initials, right? Initial means ice table. So we have our expression. Everything does need to go in our ice table, right? Because they're all aqueous. So initially, we know our copper concentration is 6.7 times 10 to the negative 4th. We know our initial ammonia is 0.11 molar. We don't have any of our complex ion, right? Because that's a product. We don't have any product right now. So that's going to be 0. Here's where it gets a little different than what we've been doing. When we do our change, so our change, we're going to be saying that most of our copper is going to react. Because see how the copper concentration is a lot less than our ammonia concentration? We're going to say most of this copper is going to react. So we're going to say approximately, we're going to decrease our copper concentration by 6.7 times 10 to the negative 4. That means our ammonia concentration also needs to decrease by that much. But of course, we had 4 ammonia, so we need to multiply by 4. And then our copper nitrate will increase by 6.7 times 10 to the negative 4th molar. We have these approximately here because what we're trying to find is what is our equilibrium concentration of copper. So that's why under our copper concentration, at equilibrium, we have an X, because that's what we're trying to solve for. So even though it looks like our initial and our change should equal 0, it doesn't actually equal 0 because not all of it will be used up. So we'll just say X for our equilibrium of copper. Our ammonia we can solve. It actually ends up being, since our concentration of our change is so small, it ends up actually just being still the 0.11 molar here. And then our complex ion formation is going to be 6.7 times 10 to the negative 4th molar. So what we can do is we have our equilibrium concentrations. We have our Kf. We can say our Kf equals, right? We wrote the expression, which is products over reactants. Plug in all your equilibrium values. So if we plug in our equilibrium values, we can then, they rearrange the equation to solve for X. That's fine. You can do it however you want. So they rearranged, they got X by itself. They plugged in the Kf value, did all of the algebra, and found that their X is 2.7 times 10 to the negative 13. So that is the concentration of copper at equilibrium. As you can see, our concentration of copper started at 6.7 times 10 to the negative 4th. Most of it was used up to make this copper ammonia complex, but we still have some left, just a little tiny bit. It's 2.7 times 10 to the negative 13. So that's a very, very small amount of copper that we have left. So that would be our concentration of copper at equilibrium. So that would be the answer. You can go back and check. As we said, That 2.7 times 10 to the negative 13th is much, much smaller than 6.7 times 10 to the negative 14th. So we made the x approximation. It works out. So the copper that is remaining is 2.7 times 10 to the negative 13th. That makes sense. Our copper concentration has to be extremely small because our formation constant was very large. Our formation constant was times 10 to the 13th. So it was a very large number. The last thing we have to do is one last practice example. So let's go ahead and pause this video, watch the next one.